Okay, so the next thing I want to talk about is exploration 2. Now, I don't remember, what does the journal say? Did you do exploration 2 or not? You were supposed to have done it? Okay. Then let's talk about our answers here. I didn't have my calculator, so I couldn't redo it. But, so it says the first part of the fundamental theorem of calculus asserts that the derivative of, so if we're going to take d by dx of the integral from a to x of f of t dt, that's going to be equal to f of x, right? That's just the fundamental theorem of calculus part 1. So in part 1 of exploration 2, it says basically to graph d by dx of the integral from 0 to x of x squared dx. So did everybody do that? Why doesn't everybody do it right now? Okay. Sure. I don't think so. I will double check that. Ask me again in physics. No, on your calc quiz, but I'll try to take care of it, check it third period. So ask me again in physics whether or not you need it. Oh dear, that's always distressful. Okay, so I'm going to do this too. So I want to take ender of fn int x squared comma x comma 0 comma x graph. Go to the error. Oh shoot. Oh, I gotta write it down. So it's n derive of fn int of x squared x 0 comma x comma x, because that's what I want to do it. I want to take it with respect to x. Is that right? Whoa. Oh, yep, that's right. So it's x squared comma x comma 0 comma x, close that comma x. Now I can graph it. What'd you get? All right. So I get something that looks like that. Is that what you get? Okay. Is that what everybody gets? Still working on it? Okay. All right. And then the second thing is to change it, the 0 to a 5, right? So this was number 1. Number 2, I seem to get the same thing. Is that what everybody else gets? All right. So that was 1 and 2. 3 is without graphing. We want to know what the x-intercept is going to be for the integral from 0 to x of x squared dx, and for 4, the integral from 5 to x of x squared dx is going to be. What are we going to get? And I'm going to graph it myself because I'm the teacher and I can do that. So what do you think it should be for this one? What should the x-intercept be? Okay. I would agree that it's 0. How about for the other one? Nothing appeared on my calculator. Well, yeah, the x-intercept is at 5. All right, so how about number 5? How does changing A affect these graphs? It doesn't. What were you going to say, Zoe? No change. Okay. And what about these graphs when we change A? Yeah, it changes it, it shifts it vertically. All right. So, if it's shifting it this way. Originally, the graph was, yeah, vertical works both ways. Okay. So, this brings us to the fundamental theorem of calculus, part 2, which basically says if we take the integral from a to b of f of x dx, that's going to be equal to the antiderivative evaluated at b minus the antiderivative evaluated at a, which if you are in AP Physics, we've done a couple of times because we've needed to, and we've kind of danced around this. We've talked about how taking the integral is taking the antiderivative. Okay, so once again, you have that written in your journal, so I'm not going to waste the time with everybody copying it down, but let's try a couple of problems. All right, so let's start with page 307, number 36. If somebody would read it for Yes, please. FN ints, it's numerical integration. Integral from of squared. Beautiful. Okay, we gotta get used to it. I should go around the room and everybody should have to read a different problem every day. Okay. So, of course, once again, just like we went over for limits the other day, and you guys were a wreck about the things we do when we approach a limit, when we approach an integral, we're going to build up a bunch of tools, a bunch of things that we're going to do. Now, one thing you can do when you come to an integral is you could graph it and find the area under the curve, because that's what an integral really is. But we're told specifically here to evaluate this using the fundamental theorem of calculus part 2, which means we are going to use the antiderivative. So the first thing you have to ask yourself is, what is the antiderivative of that? Which is precisely why you had to memorize all of those. No. No. Yes, it is in fact negative cotangent. Okay? So the antiderivative is going to be negative cotangent theta. The reason why you had to memorize all the derivatives was so that you could identify them. Remember when you had to memorize all of your multiplication facts, you had to know that 4 times 4 was 16, because then they changed the question and it was 16 divided by 4 is what? But you had to know them going forwards, the multiplication, so you could do them backwards doing the division. We're doing the division part now. But you have to know your new math facts. You might want to go back and review them. You might want to dig out that card that we made 1,000 years ago and start reviewing it again when you're brushing your teeth. Okay? So, according to the fundamental theorem of calculus, part 2, and the way I would write this is I would say this is equal to the cotangent of theta. And that's where this line comes in again that reminds me what my upper and lower limits are. I think it's important for your sake and the sake of somebody who's assessing your work that you actually write down what you think the antiderivative is. It's a good step to take instead of just jumping to the step where you're substituting values in. I just help it thinks organize. I think it helps to organize your thinking. Okay. And then we just substitute in the upper limit. So that's going to be negative cotangent 5 pi over 6 minus the lower limit subbed in, which is going to be negative cotangent pi over 6. Make sure you're in radian mode. You can use your calculator at this point. Or remember that pi over 6 is 30 degrees and cotangent is cosine over sine, and do some magic. But what are we going to get? Nope. positive 3.46? Because one of them ends up being negative. You end up with another negative sign in there based on reference angle. I think it's the 5 pi over 6. No, it's just that if you did it, if you remember in your heart that, what is it? Either the sine or the cosine of 30 is radical 3 over 2. You shouldn't.
Oh, I did pi over 6 minus 6.
So when I do it, what I did was I pulled out the negative sign. Okay. So I've got that negative sign. I have the cotangent of 5 pi over 6 is negative 1.732 minus the cotangent of pi over 6, which is positive 1.732. So when you add those, you should get your negative 3.46 whatever, but then you've got a negative sign out front. You need to respect the negative signs, as always. Okay. All right, so you do number 30. Sure. When and where? I just wasn't quite sure what you were asking. Mm-hmm. And I think there's a problem with what you're trying to do. It could be radical 3. Like you could look at this as x is radical x cubed, but there wouldn't be any square root of 3/2 there, or 2/3 or anything. So we did a whole section on antiderivatives, remember? So if I had, for instance, x to the n, and I took the derivative, what would I get? What would I do?
X to the n minus 1.
Right. Okay. So if I want to take the antiderivative of x to the n minus 1, what do I have to do? What did I do to the power when I took the derivative? I subtracted 1. So when I take the antiderivative, since I'm undoing it, I have to add 1. So the antiderivative of this is going to be x to the x minus 1 plus 1, okay, or n. But, well, I'm not even worried about the plus c right now. Okay, the plus, I'll tell you why we don't have to worry about the plus c. So this is equal to x to the n. But if I take the derivative of that, what am I going to get? If I take the derivative of this, what do I get? I get this. Is that what this looked like? No. So what do I have to do when I take the antiderivative? It's not enough to just raise the power by 1. I have to what? Divide by the new power. Well, which is effective. It's a fraction, okay? All right, so that when I take the derivative of this whole thing now and I bring my n down, it's going to cancel with the n in the denominator, and I just get that. Okay, so now that we all remember how to take an antiderivative, okay, what's the antiderivative of x to the 3/2 going to be? What am I going to do? X to the, hang on, x, I'm going to raise the power by 1, x to the 5/2, but then what do I have to divide by, Sarah? 5 over 2, which Zoe was talking about before, is the reciprocal of what's in the denominator. So it's 2/5 times x to the 5/2. And then I have to evaluate that from 0 to 5. Huh. Oh. So you did there is no negative sign.
Yeah, I know.
Okay.
I keep forgetting
Gotcha. No, which is a really good question. In this case, you do not add plus c because it's a definite integral, so I'm looking at it over an interval, so it's not a random function, it's a specific function. And because this is, like I said, a definite integral, in another week or two we will do indefinite integrals, and then we're going to need the part c because we won't be finding the area. What we're really finding is the antiderivative, an equation so that we can find the area no matter what we decide to do. Okay? All right? So we remember how to do things now? Okay. All right, let's try another one together. Let's try page 308, number 64. If somebody would read it for us, please. Maggie, would you read for us, please? Through part A. We'll pretend that didn't happen. Go ahead, start again, Maggie. Okay. So we want to find the area under that curve, right? It's an upside down parabola. I know parabolas don't really have an upside down, but it feels like it should because it's not concave up, it's concave down. Okay. It's a sad parabola. Okay. And just by looking at that, you would know that it's concave down in a sad parabola because its second derivative is equal to what? Less than 0, because there's this negative sign popping around here. And this is the only term that's going to survive to the second derivative. And the second derivative tells us what? Concavity. Okay, and it would give us the point of inflection if we set it equal to 0. Okay. All right, so if we're supposed to find the area under the curve, what does that mean? I'm taking the integral. Okay, so I'm going to take the integral from -3 to 2 of 6 minus x squared dx. And as you hopefully recall from the properties of integrals that we had earlier in this chapter, I can divide this up and integrate term by term, which I probably would want to do because this is pretty easy. All right, not easy. It's pretty straightforward. Okay. So, what's the antiderivative of 6 going to be? Not the derivative, the antiderivative. 6x. Okay. Rebecca, what's the antiderivative of x to the 1 going to be? I'm going to raise it to another power, right? So it's going to be x what? What? It's already x to the 1. So I add 1 to the power and I get x. I can't hear you with your fingers in front of your mouth. X what? Remember when we took the antiderivative back here? We added 1 to the power and then we divided by the new power, right? We divide by the new power. So if this is x to the 1, and I'm taking the antiderivative, what's my new power? Sarah, help her out. X to the 2 over 2. Okay. Rebecca, why don't you try the next one? It's x squared, so when I take the antiderivative, it becomes well, I'm going to raise the power by 1, so it's going to be x to the 3, and then I divide by the new power, which is 3. Okay, and I'm going to evaluate that from -3 to 2. Everybody see how we're doing it here? No. This is a definite integral, and when it's a definite integral, I don't have to worry about the constant because I'm evaluating it within a specific interval. Okay? So now I go through and I substitute in my 2's everywhere. So this is going to give me 12 minus 4 over 2 minus 8 over 3 minus substituting in my lower limit. So that's going to give me 6 times -3 is -18 minus 9 halves minus -27 over 3. Now, You can't simplify that. No. It's just a polynomial. Polynomials are cool. Now, for reasons of my own making, I think I'm right. I don't want you to put this into a fraction. Or, sorry, I don't want you to put it into a decimal. I want it to be a fraction. You can do it. It's good practice for doing things my way. So what you should get is 125 over 6. All right, the bell's going to ring. I want to let Miss Basili have a chance to set up her class. So